Hello, my name is Luke Kandaris, and I'm here with my teammates Sairam Revanth Palvuri and Vinay Kumar Kulguri. And this is our Group 6 feasibility project to present to Dr. Soleil and our fellow system designers. A little bit of background about the system site that we selected. So the proposed system will be at the North Temple office building in Salt Lake City, Utah, which is owned by the utility company PacifiCorp. And here off to the side, you can see the transmission network of the areas that PacifiCorp is responsible for. So you can see that they operate the power transmission network for Utah, Idaho, Wyoming, Oregon, and some parts of California and Washington. So here's a satellite view of this building complex. So here on the left-hand side, you can see the actual NTO building. And then in the very center of the image, you can see the two carports that we're going to be focusing on for this design. So here's a more zoomed in picture of this site. And you can see the carports outlined in yellow. So they're about 10 feet tall, flat on the top. They're free of obstructions and made of concrete. And they have a combined area of 2,200 square meters. And the client gave a budget for this system of $500,000, and they would like to try and meet as much of the power needs as possible while staying within this budget. So they preferred to place the PV system on the carport because it is an existing structure that is flat and free of obstructions and will be easier to mount PV system to. And here we have the utility charges for this wing of the building. So we didn't have an actual utility bill because it is owned and operated by the utility, so they don't bill themselves. But we were able to get some metering data for the meter that feeds this wing of the building. So here we can see the monthly kilowatt hour usage. And the other column of this table shows the the cost of this power use. So this cost was calculated using that kilowatt hour usage, as well as the standard commercial utility rate. And it does consider time of use charges. So it considers using 6 hours of peak rates. And then we'll move into the technical analysis of this system design. So it will go over the evaluation of the potential energy output, as well as the system's electrical compliance. And it will go over the proposed layout of the modules, inverters, and AC load center. It will also include a discussion of the site evaluation, as well as potential shading concerns.
Hi everyone, this is Sairam. So this slide explains about the monthly average irradiance at Utah. So the image shows Utah's monthly average solar irradiance. It is one of the top 10 states for the solar. As you can see, in the winter, it is just less than 100 kilowatt hour per meter square, and in the summer, it is over 200 kilowatt hour per meter square. In June, it is the highest, over 220 kilowatt hour per meter square approximately, and in the December, it's the lowest at 80 kilowatt hour per meter square. And based on its data, it is really suitable for installing a solar system. So coming to the panel selection, so the client requested using First Solar as a supplier for the panels. So the selected panel would be 06 panels. The model is FS6480C, which has a rated output of 480 watts and with an efficiency of 19%. These modules have dual junction box design, which eliminates the need for wire management and also maximizes connections between modules. The innovative speed slots offer the industry's quickest installation times by combining the robustness of bottom mounting with the speeds of top clamping with fewer fasteners. The cost of each panel is $220 or $0.46 per watt. Choosing a US manufacturer will also shorten lead times, so First Solar would be a better choice. Next slide. So coming to inverter selection, the client requested using SMA as a supplier for the inverters. So based upon the design, It has a maximum of 22 strings into one inverter according to the number of strings, and output from them we have chosen SMA's Sunny Tripower 24,000 TL US inverter, which has a rated output of 24,000 watts. So this string inverter was convenient for the number of modules in the system. So these inverters each would cost around 4,325 US dollars. Yeah, next slide. Yeah.
Now we'll be moving into the mechanical design of the system in helioscope. So here you can see our two carports with the modules laid out on them. You can also see that in the building between them, it has been modeled as a segment in order to simulate the shading. We have a total of 388 panels for a total power of 186 kilowatts. The racking type is fixed tilt set at an angle of 10 degrees in order to maximize the number of modules we can fit on each carport. And they are oriented at 180 degrees true south. It's convenient that these carports happen to be on the south end of the building because that made it easy to do that. And the modules are set back from the carport edges by 3 feet in accordance with Utah state codes. And here is our more zoomed out image of our electrical design. So you can see that where the 3 inverters are on each carport for a total of 6. And you can see the orange wires leading to the AC load center over on the right-hand side of this image, and that is where power is fed into this wing of the building. And here we have our one-line diagram. So this one-line diagram has a maximum number of strings into an inverter of 22. For the other carport, it's 21 per inverter. And between the strings and the inverters, we have our DC disconnects. And then after the inverters, we have our AC disconnects for the system. And then they continue on to the AC load center. And here we have our max voltage and current table. So this shows the max voltage and current at both the string and system level. And this, along with the wire gauge ampacity rating chart, is what drives the wire gauge selection. So here we have our max voltage per panel of 252 volts that's adjusted for temperature. And so in order to keep within the NEC guideline of being less than 1,000 volts for a commercial system, we can only fit 3 modules per string for a total system voltage of 756 volts. Because the voltage is so high on these modules, that leads the current to be lower. So calculating it using method 2 in the NEC guidelines yields around 5 amps per string and total system output of 116 amps. So from those max currents, we were able to select our wire gauges and kind of look at what our voltage loss would be. So from the string to inverter, our amperage is only 5 amps. So we could have selected a smaller wire gauge than 14, but we went with 14 wire gauge in order to reduce the system losses down to 0.1%. And then our total system max ampacity is fairly large because of our large number of strings coming in at 116 amps. So we had to select a rather large wire gauge size of 1 wire gauge, which results in voltage losses of 0.7%. And this here you can see the shading model, an isometric view of our layout with our 10-foot tall carports, as well as our building that's around 40 feet tall. So in this next slide, we can see our shading analysis and the results of it. So this system experiences shading losses of 1.2%, with the worst panels being between 6 and 7%. We decided that these losses weren't significant enough for us to remove even those panels that are experiencing the most significant losses.
So coming to the system output, the system has a DC nameplate capacity of 185.8 kilowatts, which would translate to an annual production of 294.6 megawatt hours. It has an inverter AC nameplate capacity of 144.4 kilowatts, and which would give us a DC to AC ratio of 1.29 with a performance ratio of 86.86% with a kilowatt hour per kilowatt peak value of 1586 system yield. So this 294.6 megawatt hours can provide 23.8% of this wing of the building's annual energy consumption, which is really good. Next slide. So coming to the list of components, as discussed earlier, panels were from First Solar. 388 of them were used. Based on their output, 6 inverters from SMA, Sunny Tripower 24,000 TL US were used. And as the system tilt was set at 10 degrees, Unirack's RM10 racking system was used. To hold the racking system to the roof firmly, concrete weights are required, and the other racking system components were also used, such as roof pads, racking clips, and hex bolts. Based on the helioscope output, the following wires were required: 10 American wire gauge stranded green wire and normal wire. For AC home run, 1 American wire gauge stranded wire, and for the strings, 14 American wire gauge stranded wire was used. At each of the carport, a DC disconnect panel was used, and each required 6 DC breakers. And at the AC level, a single AC panel was used from GE to connect all the outputs from the inverters, and 6 AC breakers were required for each of the inverters. Next, please. So coming to financial analysis, for this system, the client has given us a budget of $500,000. This analysis examines the cost of the system, including available tax incentives. Using that install cost and other inputs, an NPV analysis was performed. Next. So coming to the hard cost, it consists all the modules, inverters, racking system, electrical BOS, other miscellaneous items, and also contingency cost. So it's summed up to over around $200,000. So based on the NREL's data, the average cost per watt for a commercial system for a similar size is around 1.63 US dollars. For this 186 kilowatt system that was designed, it would be around 300,000 US dollars. So for this financial analysis, the actual calculated hard cost was used to be more optimistic. Next slide. So coming to the soft cost, this table was generated using the NREL's average cost per unit. So for the labor cost, it would be around $58,000. For the permitting, it would be around 18,000 US dollars. For the installation rental equipment, it would be around 8,600 US dollars. For sales tax, it's around $6,500, and all of them summing up to a total of 90,640 US dollars for soft costs.
This is Vinay Kumar, and I will be continuing on the financial analysis. So, coming to the incentives, the federal tax credit of 30% of the system cost is applicable for the every state. For commercial scale projects, the state of Utah has a renewable energy technology tax credit of 10% of the system cost or $50,000, whichever is less. In this case, 10% of the system cost is less than $50,000. So the total incentives will sum up to 40% of the system cost, which is $116,000. The state of Utah does not have any solar energy renewable credit program. So the next slide, the maintenance cost. As per the NREL data, the cost of operation and maintenance for the year 2021 is $19 per kilowatt AC. So we have an AC output of 144.4 kilowatt AC from the helioscope. Multiplying these two will get the annual maintenance cost, which is at $2,743. So coming to the next slide, inputs for financial models. So for the NPV model, which is net present value, we created three models with two tables for necessary inputs. The first table contains the constant factors that are not varied. The second table contains the variable factors that are changed for the three scenarios. So here are the tables. The constant inputs for net present value. These factors were kept constant while performing NPV. As we know, the system size is 186 kilowatts, and the net system cost after incentives made up to around $174,000. The income tax rate is at 26%. Inverter replacement cost is estimated at 20% of the system size, which made out to $37,200. Even though we have the actual inverter cost, which is less than the estimated cost, so we have considered the estimated cost as a estimated cost of $37,000, as the cost might increase in the future. Coming to the annual maintenance cost, as we discussed, is at $2,743 and estimated extra property tax of $3,000. So the next slide will be discussing about variable inputs and NPV result table. So the three models considered for NPV are conservative, likely, and optimistic. These are the inputs which vary for the different models. The inflation rate is set at 2% for conservative, 2.4 for likely, and optimistic. The unit energy cost is set at $0.05 per kilowatt hour for conservative and $0.06 for likely and $0.07 per kilowatt hour for optimistic. The market discount rate varied at 3.5 and 4, 3.5 and 3% for conservative, likely, and optimistic respectively. Long-term consider was 20 years for conservative and 25 years for likely and optimistic. After all these inputs, this resulted an NPV of around negative $19,000 for conservative model and $52,000 for likely and around $119,000 for optimistic model. So based on the results, the next slide we're going to discuss about NPV discussions. The positive outcomes of the NPV model represent that the installation of the current PV system is profitable in the future. So the likely NPV model gives us around $52,000 of PW annual saving after 25 years. So PW refers to present worth annual saving. Whereas in optimistic NPV model, the system achieved an NPV of $119,000. So yeah, the recommendations. Based on the study and the data mentioned earlier, we would recommend that for the Pacific Corp moved forward with developing and installing the proposed carport PV system. The system is expected to meet 23.8% of energy use of the wing of the building. Using the likely scenario, this system has a positive NPV after 25 years, which is around $52,000. So after the feasible study, we recommend to the Pacific Corp to contact a local installation firm to get more accurate information on system pricing and the expected project timeline. Thank you. So these are the references we used for the feasible study. Thank you.